Okay, hi everyone. This was question 5, I think, on that BMO paper I popped up on the extension classes the other day. This one plagued me, it really did. I actually started doing this question about 5 years ago. I remember it because I brought in that BMO paper. It was when my daughter was being born. I figured that it can take hours, this kind of thing. So I took the paper into the hospital and I worked through the first four questions quite successfully. I think, anyway. I haven't managed to check my answers. I don't know if it mentions it on where I've posted the questions, but there is a book with solutions to all these questions, but it costs £51. And I'm just too stingy to pony up the money and pay pay to see the solutions. I'm pretty sure my first four are correct, but this one got the better of me. So I had a look at it again the other day, thinking, never give up on these kind of questions. And I want to show you my first failed attempt where I sort of answered half of it, but it just didn't seem to. I just kind of got lost in a mathematical fog. And then I want to show you how to do it successfully using something called well, I normally just refer to it as geometric mean and arithmetic mean inequality, but there's a couple of other inequalities as well, which are really, really useful and just make this problem simple. And I think it's worth mentioning because apparently, and this is completely news to me, but certainly on Wikipedia, when they discuss these inequalities, it says right at the top, these are frequently used in mathematical competitions. And it was like, I didn't realize that. They're really, really handy. So it was one of those situations of like, why am I not aware, or much more aware anyway, of these inequalities? Full credit as well to Arpatha, who gave me the idea for using these inequalities. She mentioned it. I hadn't really thought about doing it. And as soon as I started using those, the answers dropped out really, really quickly. So yeah, well played, Arpatha. That was yeah, a great bit of an inspirational move. Okay, let me show you the failed attempt first, because I always think it's important to look at failed attempts, just to kind of like, ask yourself, why do they fail? I'm still not entirely sure why it fails on the XYZ. It answers part two, but it doesn't answer part one. But I still want to talk about it because I thought it was quite a good idea, even if it's a failed attempt. Um, Basically, my failed attempt was thinking, look at these. These all look like exactly what they look like the relationship that we have for cubic roots and the coefficients of the cubic polynomial. Yeah. So what I did was I said, okay, let's um let's assume that x, y, and z are the roots of a cubic polynomial, and I just was like, okay, I'll call it p cubed plus bp squared plus cp plus d equals 0. Yeah. Now, I want to talk about that assumption. What I'm basically saying is if x, y, and z are positive real numbers, then they could certainly be the roots of a cubic. Now, can the roots of a cubic be anywhere along the x-axis? Well, yeah, sure they can. They can be anywhere along the positive x-axis because, the cubic could be, p minus x multiplied by p minus y multiplied by p minus z equals 0. Yeah, that's perfectly reasonable to say that a cubic can be of that form. Now you might think, well, why have I done that? Well, it's because we already have then conditions for xy plus yz plus xz, because that's going to be in this formula, your minus b over 1. Your x plus y plus z, I apologize, is minus b over 1. Your xy plus yz plus xz is c divided by 1, which is just c. And your xyz is minus d divided by 1, which is just minus d. So it gives us something to work with. So that's what I was first thinking for my failed attempt. And you can see quite clearly here, actually, that minus x times minus y times minus z should give you your positive d. And that's why d does indeed equal minus x, y, z. But yeah, so that was my thinking. And then I thought, now I've just got to make sure that all three roots exist and are real. Yeah, because these are positive real numbers. So obviously cubics can be like that, yeah? Oh, sorry, I didn't mean to do that. Like that, yeah? And that would only have one real root, so I want to avoid that situation. So how can I do that? Well, firstly, I wrote out, let me just write out what what my thinking has been so far. My thinking is basically, okay, if I let it be the roots of a cubic polynomial, then what would I have? I would have that x plus y plus z is minus b over a, or minus b over 1, which is just minus b, obviously. Similarly, xy plus yz plus xz is c, divided by 1 if you like, and xyz is minus d, yeah? I just thought that was a good place to start, because straight away then with c, I can say, okay, so c is trapped between a third and 3, yeah? And now I can work with that and work with, say, b. Now, the one thing I need to make sure of with my cubic polynomial, because x, y, and z are positive real numbers, I need to make sure that the roots of my polynomial are positive real numbers. So how did I do that? Well, what I said was, okay, basically for cubics, there's three possibilities. You could have two turning points, yeah, one of which is above the x-axis, so one of which is positive and one of which is below the x-axis, and I'm talking about the turning points here. Provided you've got two turning points, one above and one below the x-axis, then you've definitely got three real roots. The only other way you can get three real roots is if all the roots are the same and repeated, and that happens, well, if we think about the simple case where the root is just x equals 0, when you've got just one turning point on your cubic, or if you like, where the gradient's only 0 once, and crucially, that gradient is 0 on the x-axis, yeah? If you don't have any turning points, if you've got a cubic which is kind of like that, which is perfectly possible, you will not get, it's impossible to get, I'm sure you'll agree, three real roots. Yeah? So the first thing I said was I need to make sure that my cubic doesn't have no turning points. Yeah? Now, how can I do that? Well, calculus, basically. So what did I do? I said, okay, what is my equation? So let's just get rid of these. That was just my explanation. So I need at least one turning point. I hope you can see that. I need at least one turning point. So let's make sure of that first. So we've got, if you like, what? Oh no, let's not use y because we've already used the letter y. Let's use a equals p cubed plus bp squared plus cp plus d. So dA by dP is 3p squared plus 2bp plus c. And now I can set that equal to 0 because I'm looking for turning points, if you like. bp plus c. And I can subsequently determine what the conditions are for that to have at least one turning point. So if it's got at least one turning point, if it has at least one solution, if it has at least one solution, then the discriminant of this should be greater than or equal to 0. So I was like 2p squared minus, 2b squared. That is a quadratic in p. Silly me. So 2b squared minus 4 times 3 times c. That's got to be greater than or equal to 0. Yeah? Okay, that's great, because that gives us, like, in many ways, our first answer, because we get 4b squared minus 12c is greater than or equal to 0. So b squared is greater than or equal to 3c. Now, remember that c was bounded between a third and 3. So 3c is bounded between 1 and 9. Yeah. Now, if this number is trapped between 1 and 9, and b squared's definitely bigger than this number, or equal to it, then b squared is greater than or equal to 1, and hence either b is less than or equal to minus 1, or b is greater than or equal to 1. I think actually b will be less than or equal to minus 1, because if you remember, minus b is x plus y plus z, and x, y, and z are all positive. So actually I think we need this one. But after we times it by minus 1 both sides, we can conclude that minus b is greater than or equal to 1, and therefore x plus y plus z must be greater than or equal to 1. Yeah, so it actually gives me, because that's actually the answer, I'm pretty sure that's the answer. This kind of question, it's very easy to kind of like check values and see which answers work. It gave me that answer first. Now, I'd really like to follow up on this method and also deduce Z. There's several paths open to me because if you look, I haven't actually guaranteed that in the case where there's two turning points, that one turning point lies above the x-axis and another turning point lies below the axis. That may be what helps me. In fact, I'm certain it's what helps me determine the conditions on x, y, and z, on x times y times z, because x times y times z is in fact d, and d is just the intercept on the y-axis. In other words, d just lifts the graph up and down. And so if I lift that graph up and down and it's got two turning points, I can always make sure it will have three real roots then. I've tried with the algebra, but I've been butting my head against the wall. But I just wanted to talk to you about what my first approach was, just because, you know, it might be useful. The reason why it seems to be failing for me at the moment is just because I just seem to end up with an algebraic mess. I really do. Because what I have to do then is I have to find the x coordinates of the turning points. Okay, that's fine. I can do that by setting this, you know, using quadratic formula on that. But then I've got to plug it back into this formula to make sure a is positive on one side of the root, negative on the other. And that's where it all starts going hideously wrong. Um, I'm going to keep trying to work with that way though, because I like, you know, when you get attached to a method, and I've invested hours and hours and hours now on it, and I will refuse to like see that as a complete waste of time. So I'm going to try and still see it through using my initial approach. But can I show you the approach I should have took, like method 2, which succeeded? Because it's so much easier. If you're allowed to use, as in fact you are, it would seem, these trendy little inequalities, which I know I've seen them mentioned as well on step solutions before, saying some students chose to use this. I was aware anyway of certainly two of them. I was very aware of two of them because it's quite a famous inequality, but I was unaware of the other two. So let's have a look at this. Yeah, this is known apparently as the QM AM. Oh, GM HM inequality. I've just always heard of the AM-GM inequality, but these other two are dead handy, certainly in our situation. Yeah. Now, this inequality, I mean, this is called well, let's start from the left-hand side. This is called quadratic mean or root mean square mean, but let's call it just quadratic mean because it looks quadratic because it's squared. This is the arithmetic mean. It's a sum of, you know, add up a load of numbers and divide by the number of numbers. It's the mean as we normally understand it. This is the geometric mean, which is where you times a list of numbers together and then nth root it. Yeah, and I hope you can see the relationship between arithmetic series and geometric series there. You know, one is adding, one is timesing. And then finally, we've got this much more obscure one, the harmonic mean. A harmonic series is like a series like this. Yeah, you know, it's a reciprocal series, and that's why it's called the harmonic mean here, because they're all reciprocals. Harmonics, generally speaking, you know, deals with reciprocals in mathematics. So that's called the harmonic mean, that last one. Anyway, proving these, actually, I don't think they're massively difficult results to prove. And I wonder, actually, in these tests, would you have to demonstrate with a proof that the inequality holds, and then you can use it no problem at all? I need to look further into that, into detail into that. Hopefully not, but even if you do, they're not that difficult to prove. But I'm going to do the proofs of these for another video, yeah? I promise you I will prove them all. I'd like to do it, though, once you've done induction, because I think with induction they'll be proved pretty quickly. Anyway, why does this help us? Let's just state the question again. We've got a third is less than or equal to xy plus yz plus xz. Oh, is less than or equal to 3. Remember, x, y, and z are all positive. By the way, these only hold if x1 to xn are positive, yeah? Obviously, the geometric mean gets messed up if you've suddenly got three negatives and you're trying to... actually, no, it's... I'm wondering now if they do hold. I'm pretty sure these only hold when the x values are strictly positive. I'll need to check that though, because I'm suddenly thinking actually, well, let's just see if it holds when like we've got -2, minus 3 and minus 4, for example. We'd have minus 2 plus minus 3 plus minus 4 divided by 3. What's that going to be? Minus 9 over 3, which is minus 3. That's for the AM. I'm just checking the AM here. For the GM, we'd have the cube root of minus 2 times minus 3 times minus 4. That's going to be minus 24. Cube root of minus 24, think of a cube root close to that, 27. It's going to be just under minus 3. So it's going to be like minus 2 point, 2.8 or something like that, I think. Okay, so is minus 3 greater than or equal to minus 2.8? No, it messes it up, the negative, yeah. I was pretty certain of that. I just wanted to check. It suddenly occurred to me into my head, oh, all right, do these work in the negative as well? No, they don't hold when x1, x2, x3 up to xn are negative. They only hold for positive values. But that's exactly what we've got here in our question, so we're all good, yeah? Anyway, I've been waffling on about these formulas for a while now. I'd love to prove them to you, like I say, and I will do in another video. How are they really helpful here? Well, really, the question's simple now, yeah? Because all I'm going to do is just straight away divide by 3. And the reason I'm dividing by 3 is because I want to apply this arithmetic mean one, this one here, I want to apply that one. And I can apply that one because treat xy as your x1, treat yz as your x2, treat xz as your x3. And then I can just say, well, okay, just taking the left-hand side, sorry, the right-hand side of this inequality, just looking at this, we can say we know that xy plus yz plus xz over 3 is less than or equal to 1. And it might help actually if I write it the other way around. But we also know that the nth root of xy times yz times xz is less than or equal to xy plus yz plus xz divided by 3. Yeah? That's just from the arithmetic mean, geometric mean inequality. Well, we know this is definitely less than or equal to 1, and that's definitely less than or equal to that, which means we know we can say that this here is definitely less than or equal to 1, yeah? Great. Okay, now the answer is going to pop out. Oh, sorry, that should be 3, yeah? Okay, the cube root of x squared, yz squared, no, z squared is less than or equal to 1. Cube both sides as it's strictly positive. X squared, y squared, z squared is less than or equal to 1. And then square root, we can say that x, y, z. Be careful when, doing certain operations around less than or equal to, but because x, y, and z are all strictly positive, I can now argue, okay, x, y, z is less than or equal to 1. And I've got my first answer straight away. That was something which I just couldn't solve either with the, with the other one. Now, just to show you can get the second answer no problem as well, using similar approaches, really. What did I do for this one? And I'm guessing as well, because I managed to find this answer in 2 different ways using this approach. I even used the harmonic mean and got the same answer. So you can definitely do it in other ways, yeah. So okay, that's one. That's the first part done. That's part 1 for finding x, y, z and done in that problem. For part 2, we can use the quadratic mean and arithmetic mean, because what I could say is, okay, I know. Firstly, I'm going to start by noting that x plus y plus z all squared is x squared plus y squared plus z squared plus 2, and let me just budge up and move over slightly here, plus 2 xy plus yz plus zx. Multiply out the brackets if you don't believe me. That kind of stuff comes up all the time, once again, in the roots of polynomials chapter. And it's why I think this question can definitely be done with roots of polynomials, but I'm just struggling to do it with roots of polynomials. I wish people had told me about these handy inequalities for mathematical competitions. Like, why am I blaming other people though? It's my own ignorance, Apparently, there's another really handy inequality called Cauchy-Schwarz, which I need to also look into using, because the inequality questions pop up all the time in the extension papers. They really do. So this could be really, really useful. Okay, so I've noted that. How is that useful? Well, what I could say is that we can see straight away, thanks to this inequality, that x plus y plus z, let's write it down. We know that x squared, the square root of x squared plus y squared plus z squared over 3 square rooted. So I'm using this one, yeah? That must be greater than or equal to. Now I'm going to use the AM inequality, x plus y plus z over 3. I can square both sides then, since both sides are strictly positive, and I can get x squared plus y squared plus z squared over 3 is greater than or equal to x plus y plus z all squared over 9. And a little bit of rearranging and a little bit of fiddling around is going to give me, if I times both sides by 3 and then rearrange a little bit, I'm going to have x plus y plus z. Well, let's times both sides by 9 actually. So I'm going to have 3x squared plus y squared plus z squared is greater than or equal to x plus y plus z all squared. I can use this inequality though, can't I? And I'm going to get 3x squared plus y squared plus z squared is greater than or equal to. Now if I use this fact, x squared plus y squared plus z squared plus 2xy plus yz plus zx. And I'm not saying this is the only way to do it. There's probably a quicker way. It's not mega long though, this really. I then just subtracted yeah, I've got that all right. Yeah, that looks good. That looks good. I times that by 9. I times that by 9. I've got 3 there. Lovely. Okay, I can then just take that away from that to give me, because there's a 1x squared plus y squared plus z squared and a 3x squared, I could say 2x squared plus y squared plus z squared is greater than or equal to 2xy plus yz plus zx. Cross out the 2's. I've then got that. X squared plus y squared plus z squared is going to be less than or equal to xy plus yz plus zx. I think I should actually rewrite this now as x plus y plus z all squared minus 2xyz. Yeah, I feel like I've actually gone sort of forwards and backwards here, so apologies if I've kind of messed it up slightly. But I'm going to write this as x plus y plus z, because that's what I'm looking for, all squared minus 2xy plus yz plus zx. Yeah, this is now good. Is greater than or equal to xy plus yz plus zx. Take it onto the other side, and then I've got my x plus y plus z in terms of an inequality, which I already have conditions on. 3xy plus yz plus zx. Lovely, because I know that this, remember, a third was less than or equal to xy plus yz plus zx. This is like your C in the last example. So 3 times it is definitely going to be between 1 and 9. And so as we're looking for what x plus y plus z squared is greater than or equal to, we can see that this is definitely trapped between 1 and 9, and this is definitely larger than it. So you can see that x plus y plus z all squared must be larger than or equal to 1. Because that's always larger than or equal to 1. Remember as well, with all these inequalities, and I should have said this right at the start, and I'm annoyed that I didn't. Well, I'll go back to that in 1 second. So I've got x plus y plus z all squared is greater than or equal to 1. And so finally, x plus y plus z square root is greater than or equal to 1. and that is the other side of the answer. Now, I've been through loads of different values of x, y, and z to check that these two conditions work, and they do seem to. So we've got x, y, z, they multiply and are definitely less than or equal to 1, but x plus y plus z, when you add them together, they're definitely greater than or equal to 1. Now, it is important that these inequalities are or equal to. It is an or equal to case, because you can always point out that this whole thing, the marvelous thing about the QMAM GMHM thing, is that the equality case holds when x equals x1 equals x2 equals all the way up to xn, yeah? Or in our situation, when x equals y equals z, yeah? The equality case holds in that situation. Now look at what we were just doing, because I just want to justify it's definitely less than or equal to 1, because it could be equal to 1, yeah? And I'll show you the case when it's equal to 1 is when x equals y equals z. So if we go back to our question, and I'll give you question was stated up here. When x equals y equals z, what we've essentially got there is x squared plus x squared plus x squared, in other words, 3x squared, and therefore x squared itself is going to be trapped between 1/9 and 1. And if x squared is trapped between 1/9 and 1, oh, yeah, when they're all equal, what you'll have is all the equality cases holding later on. So what do I mean by that? Sorry, yeah, that's right, x squared. Square root it, you're going to get, because x is strictly positive, 1/3 is less than or equal to x, which is less than or equal to 1. So if we pick any value for x between 1/3 and 1, yeah, let's say x is 1, and y is 1, and z is 1. Clearly we've got to 3 there, yeah? Well, sure enough, x, y, z equal to 1. Yeah, and so you get the equality case holding when x equals 1. If we instead pick, though, x is 1/3 and y is 1/3 and z is 1/3, clearly we get 1/3 times 1/3, which is 1/9, plus 1/3 times 1/3, which is 1/9, plus 1/3 times 1/3, which is 1/9. That adds up to 3/9, which is 1/3. So we're now getting the lower boundary holding. And sure enough, in our later one, x plus y plus z is plus 1/3 plus 1/3. So this holds the equality case, if you like. And it's always a really good idea to state the equality cases, because it stops certain blunders happening. Yeah, that's when the equality case holds, but when they're all the same. Here it would be when x equals 1, y equals 1, and z equals 1. Just to show you that we can get as low as that, but otherwise equality holds. We can get as high as that, I should say. We can get to 1, but otherwise when you times them all together, it will definitely be less than or equal to 1, thanks to the QMAM GMHM inequalities. So it's much easier with that's the way I did it. I feel like I faffed around a lot there. I bet there's much simpler, quicker. I bet you rather than the 8 or 9 I've used there. And yeah, I want to talk some more really to you all about why with those inequalities it's important to identify the equality cases, because if you look here, all of those are equal. Like, work it out with x1 up to xm, where each one is exactly the same. So if you've got like x1 equals x2 equals x3 equals x4 and then is 4, you'll see all of them end up equaling x, yeah, because you get 4x over 4, which is x. You get x to the power of 4, but to the power of a quarter. That's x. You'll get 1 over x plus 1 over x plus 1 over x plus 1 over x, which is obviously 4 over x. But if you're doing 4 divided by 4 over x, you get x. And once again, we've got, what have we got here? Uh, x squared plus x squared plus x squared plus x squared, which is 4x squared divided by 4, which is just x squared square rooted. You get x again. So the equality case holds when they're all equal. And so they're dead handy inequalities to use. They really are. And I recognize that now, and I wish I'd been using them for years, but I haven't. Dead handy. Really, really handy. Okay, I hope that was useful. I've got to go and mow the grass, so I will bid you farewell.